Hi, in this video we're going to look at a new concept called compatibility. Before we get into compatibility, I kind of want to go through this lecture with some storytelling. So first one, I want to start with um, a scenario where you have a bar that it's anchored here, and you have a force that's applied at B. It's called as P. Okay, that's the only external force, and let's see if we can solve it. When you look at this, you obviously see there are two sections, AB and BC. And if we do that, if you look at AB section, and we're gonna cut anywhere between A and B, then we will be able to, for example, if I look at the right section, because if I want to avoid finding the reaction support at A, then I will have look at the right section. This is our B and this is our C, and there's a force applied at B, which is on the right section. All right, so in that situation, if I were to using a red color to indicate what's the internal force at this cut, that's going to have to be pulling to the left and equal as P, and that's going to be in tension, right? Okay, so in that situation, our delta AB section, we'll look at this yellow highlight, and that will be P, that's going to be internal force, times L, and remember we're looking at AB section, that'd be LAB over AE, okay? Now if we were looking at another section, we're looking at BC section, and now we're going to cut anywhere between B and C. So if I do that, again, I choose to look at the right section, trying to avoid finding reaction at A. Then we have C here, and do we have any force supply at this section? No, even though there's an arrow, this might pass this point we talked about before, but this force is applied at B, so there's no force acting at this one. So the internal force here is 0. So delta at BC section deformation is 0. Okay, so now if we're going to look at this entire bar ABC together, that's deformation is going to be summation of them, of those two sections, and that will give us P L AB over AE. So take a look at it. So in this final equation, the length really matters. It's only LAB. Okay, only AB section it matters. BC section is not showing up in the equation. Okay, so that's the first one. And the second scenario I want to introduce is I have the same bar ABC. However, this time the fixed support is happening at C. Okay, so we have ABC, but it's fixed at C now. What do you think this is gonna happen? We're gonna use the same logic, and we also have two sections AB, and also we have a section of BC. Now, if we were cut anywhere between A and B, for example there, and I'm going to look at the left section, A. So what do you think? Is there any force acting on this section? No, because there's nothing on here because the external force is applied at B. So in that situation, my internal force here is 0. Then my delta AB, my deformation in the AB section is 0 since there's no internal force on it. However, if I were going to cut anywhere between B and C, so if I were cut here, and I look at the left section, A, B has a force P there, and C, okay, I don't have C because C is, so if I cut over here, what would be the internal force at here? That's gonna have to be equal, but opposite would be P, and that's a compression, right? So in that situation, my delta BC, this green highlight area, is gonna have its own contraction, deformation. That's negative. Its internal force is P, and L, what's L here? It's LBC over AE. Now we're gonna combine them together to look at this entire bar. So it's gonna be PL over AE sigma, and that will be equal to negative PLAB over AE. Right? So now let's look at this compared to this one. Well, one is contraction, one is tension, and another one, the difference is, oops, I wrote it wrong. This is BC. It's in length what matters. And here, BC length matters. However, here, AB length matters. Here, I encourage you to visualize that. If I have a force supply at B, what really is elongated is AB section. And here, if you have forces applied at B here, what section that's being contracted? It's only BC. So now I actually help you validate this formula you derived. Okay, so far, hasn't get into a new topic yet. Like I said at the beginning, it's a storytelling, and I think I'm getting there now. What I'm going to bring is the third scenario. This time is different. This bar ABC is completely anchored between those two walls. And then we have a force also acting at BP. So again, I want to use your imagination. Think about it. If this bar is anchored between two walls and I have a force at B, it's pulling it towards C. Use your intuition. What do you think the force acting at A, what's the direction going to be? If I'm pulling it to the right and the wall is going to say, I'm going to push you back, right? So that's AB. It's going to be, we're going to call this side PAB. Then at C part, at the C end, it's being pushing into it, and the wall is going to pushing it back intuitively. So that's going to be PBC. That helps us identify those two directions. And we do not know either one of those two reaction force at the wall. So using our static concept, we're going to write down forces at X direction because that's what we have. So force at the X direction, we have P, and to the left, we have PAB, and minus PBC. That equal to 0. And the force at Y doesn't give us anything, right? There's no force at Y. How about if we do moment about? If we do moment about anything, they go across, it's at the same line. That does not help you with anything. So we only have this one equation. So let's make a point. We have only one equilibrium equation. However, we have two unknowns. We have never seen this before. And we call this, because we know if you need to solve two unknowns, you need to have two equations. So we call this static indeterminate. In other words, static equation cannot help us determine the answer here. And that's a new topic. That's why we need to use this new concept called compatibility equations. So what's this compatibility equation can help us solve those two unknowns? We're going to relate to our axial deformation. Okay, so now let's thinking about it. If I were cut, again, we have two sections. We have AB section and we also have a BC section. All right. Okay, so we have AB and BC section. If I were to go ahead and cut anywhere between my AB section, and I'm going to create my FBD, I'm using the left side. We'll have this external force PAB here through the wall. And then we need to figure out the internal loading at AB, and this will have to be equal to PAB, this internal loading, and that's in tension. And what will be the deformation here? So delta AB section, is green highlight, is gonna be subjected to elongation, so that's gonna be force, internal force is PAB, and the section length is LAB, and divided by AE. Now if we're going to look at the BC section, if we cut it randomly between there, and what we have. And we will cut at BC section. Then we're going to look at this area, and if we look at the right section, we have over here. We have external force from the wall, that's PBC. And then we want to figure out what's going to be the internal force. Internal force have to be going that way to balance it. That's PBC. And that's going to be our compression. It's compress that section. So in that situation, we can write it down. Delta BC section, this red highlighted area, it's subjected to contraction, so it's negative. And the internal force is PBC. And L, the length is LBC. The entire length is LBC here over AE. So we got those two deformation for each section. And what can we thinking about? This entire bar is stuck between those two walls. So if you think about this entire bar delta, which is summation of this PL over AE sigma, what's this value have to be? 0. You're right. Because it's stuck between the two walls, it's not going to have any change in deformation. So in that case, you could write this down. We're going to bring delta AB and delta BC here. So PAB, LAB over AE minus PBC, LBC, LAE, that equal to 0. And you can, okay, so now we can actually cancel out AE, and we will have our second equation through this axial deformation. And so we'll have PAB times LAB equals PBC times LBC. That's our second equation. And then go back to our first equation here, and that's our static equation. Earlier we were stuck on here and determined this is not solvable with one equation and two unknowns, Now we actually have our second equation. We can solve our PAB and PBC using this equation. So we call this equation called a compatibility equation. Alright, so that's how we solve this one. And in the next example, I will show you actual example how to do this. Okay, I'll see you on the next one. Bye.